Welcome back to Educator.com and our series on AP Computer Science. Today's lesson is on sorting. We'll first talk about sorting, what it is, and the general idea of how to accomplish it, and then we'll look at 4 specific sorting methods, three of which you'll need to know for the AP exam, and the 4th of which is not covered on the AP exam, but is still a very good sorting algorithm to be familiar with. So we'll first talk about sorting, and then the 3 methods of sorting that are on the exam are selection sort, insertion sort, and merge sort. The 4th one that we'll talk about, quick sort, is the one that's not on the exam, but still very useful and good to have at least a brief understanding of. Sorting is one of the most important applications in computer software. And sorting is basically putting the items in a collection in order. It can either be ascending order or descending order. And you can sort any of the following. You can sort integers, doubles, strings, and actually you can sort just about anything. You can sort any class that implements the comparable interface. The comparable interface has a method called compare_to, and compare_to results in a value being returned to the calling program that indicates whether one value is less than, greater than, or equal to a second value. We've seen this in the lesson on strings. Strings implement the comparable interface and therefore have a compare_to method, and we can compare 2 strings to one another, and if the return value is less than 0, it means the first string sorts before the second string in the sort order. If compare_to returns a value greater than 0, it indicates that the second string sorts after the first string in the sort sequence, and if it returns exactly 0, it means that the 2 strings are identical and they would have exactly the same position in the sort sequence. So we can really sort anything, and if we create a custom class, and as long as we implement the comparable interface and thus provide a compare_to method, anyone using our class can sort objects of the type of our class simply by relying on the compare_to method that we've provided to tell between 2 objects of that class which one should sort before the other one, or if they're equal. There are actually many sorting algorithms, and they vary in efficiency and complexity. And generally, as with most things in software development, the more efficient algorithms are a little bit more complex to implement, and the ones that are simplest to implement won't give you quite the best performance. So there's always going to be a trade-off there, and which one to select will vary depending on what you're attempting to do and what your application is. And we'll talk about that later in the lesson. But this lesson covers the 3 sorting algorithms you need to know for the AP exam, plus 1 more. So let's get started. The first sorting method that we'll talk about, and this is one of the 3 that is covered on the AP exam, is called selection sort. And selection sort is known as a quadratic sorting algorithm. If you remember from algebra, a quadratic function has a power of 2. The highest power of the function f of x would be x squared. So a quadratic algorithm means that if you have a set of n items, the worst case performance, meaning the longest it could possibly take to sort, would be n squared operations, thus the term quadratic. In computer science, we use something called the big O notation to indicate the performance of an algorithm. And big O stands for order, and this algorithm would be an order n squared algorithm, meaning that for a set of n items, the worst case performance would be n squared operations to be able to sort n items. Generally, your quadratic sorts or your order n squared sorts are going to be your least efficient sorting algorithms. But on the other hand, probably the simplest to implement. Selection sort is known as a search and swap algorithm. What we do is we find the smallest element in the array and exchange it with the element that's in the first position. This is assuming that we're sorting in ascending order, which is by far the most common order. The smallest element in the array should go in the first position in the array. Now technically that's position number 0, but I'm going to refer to it as the first position in the array because that's the terminology that makes the most sense to the most people. So the smallest element belongs in the first position. Ultimately, the largest element in the array would go in the last position. But we're working from smallest to largest. So we find the smallest element in the array, and because the array is not sorted, that takes potentially n comparisons to find the smallest element. And then we exchange the smallest element with whatever element is currently in the first position. That puts the smallest element in the correct position in sorted order. And whatever used to be in the first position just switches places with wherever the smallest element used to be. So we're building the sorted array from the front end of the array to the back end. Or if you think of it graphically, we're building it from left to right. If left is the lower numbered positions in the array and right is the higher numbered positions. And then we just repeat until we reach the end of the array. So find the second smallest element in the array, which would be the smallest element that we haven't already moved to the front of the array, and we exchange it with the element in the second position. So then positions 1 and 2 would have the smallest and second smallest elements respectively, and whatever was in position 2, in the second position, is now ends up in whatever position the second smallest element was originally in. And so on, and we repeat until all the elements are in order, which means until we've reached the end of the array. Since it takes n comparisons to find the smallest element in an array of n elements, and we then have to move each of those n elements, that's where the n squared performance comes from.